Good morning to everyone. So the first slide was who I am, but Ernest already said everything. So no, yes, I'm well known for my work in PyPy, and in general I like working with compiler languages, low-level stuff, and that's why I ended up trying to understand what is the problem with C extension in the Python community and the Python ecosystem. Among the other things, I recently started my new job at Anaconda. Now I'm also a PyScript maintainer, which is like Python in the browser, and you should really go tomorrow at Fabio's keynote, which is in the morning, okay, but check it out. Who are you? I mean, this talk is labeled as advanced, but well, it's hard to understand what is the audience. So I wrote this talk with the assumption that you have a vague understanding of what is like Python.h. Like if you have to write C extension by hand, how it works, what you have to do, and I mean, this is the starting point. And you have to know a bit of C to understand what I'm going to talk about. I hope that many of you know these things. They'll say, who doesn't know anything about the stuff which is written here? Okay. Okay, I will try to make it understandable anyway.
Ask the other way around.
Who knows everything? Good. So, okay, let's start by the problem. I wanted to label this slide like the biggest problem in the Python ecosystem you don't know about. It's something that not many people think about. But imagine a world in which we can try many things, like CPython can try to remove the GIL. They tried new optimization, they tried target pointers, and everything makes fast. Or we try, for example, to write a new Python interpreter, maybe written in Python itself, with a JIT compiler and everything is fast and everything works. It would be nice if everything worked, but we have problems. One of the problems that doesn't allow all the things that I'm talking about is this Python C API, which is not a problem, like it's a terrific piece. It's an important part of the Python ecosystem and why Python is so successful. It's what enabled many authors to write good libraries. For example, Numpy, SciPy, Cython, Pandas, PyTorch. All the data science stack relies on this Python C API, which is the way so that you can write extension in C and integrate with Python interpreter and everything works. But the problem is that because of history, this API is too tied to the CPython internals. Now we are stuck at the point in which if you try to change anything or almost anything inside the CPython itself, you break something. So it's very hard to evolve the CPython implementation itself. And it's also incredibly hard for alternative implementations, for example, PyPy, which is where I'm coming from, because in order to use C extension, you have to emulate all the internal details of CPython, and you do it. And to do that, it's hard and slow, and you lose a lot of time. When I say that that the C API exposes internal details, what does it mean? The biggest problem, one of the biggest problems is reference counting. CPython, the CPython implementation relies on reference counting to manage lifetime of objects, and this is really exposed in the C extensions because you have to do PyIncref and PyDecref all the time. And if you want to remove reference counting and use another technique to manage memory, this becomes a problem because all your code around, relies on this. The other problem is that objects, they are not abstract. Like in the C code, you pass around these PyObject star pointers, and it's just a pointer to a place in memory where the object lives. And like if you have two objects and you have the same object and you pass it twice to the function, we expect that you get the very same pointer. So you can, for example, compare by equality in C, and it's a pointer comparison, and it's the same as Python level identity. But it is also a problem because sometimes you don't have an object to pass around. For example, in PyPy, we have an optimization in which if you have a list of integers, these are stored as raw values without having an object. So what if you pass this object to the C? Suddenly, we have to create a proxy to pretend that we are an object, but we are not, and this becomes complex and slow and everything. So this kind of stuff makes everything hard. And or the other another exposed details is that structures are not opaque. So you have a PyObject to start around, and you can access the field ob_ref_count or ob_type, which means that it needs to be at this specific point in memory. And if you want to try another structure of objects which doesn't have ob_type at that point in memory because you because you want to optimize it another way, well, you cannot because all the code around expects it. So this is the kind of details that it would be nice if they were not exposed. As I said, yes, reference counting is a big problem. A big misunderstanding when we talk about garbage collectors is that, well, the name is wrong. The garbage collector is not about collecting garbages, it's about managing memory. It should be really called memory manager. It's the piece of software which takes care of the lifetime of your object and makes sure that you don't, well, you reclaim memory when it's no longer needed. And state-of-the-art garbage collectors are very, very fast. You can have super fast allocation, fast deallocation, incremental collection, so you don't have pauses. Like in the Java world, they have a lot of very good GC. PyPy has a not too bad GC. CPython relies on reference counting, as I said, but it has pros and cons. Sometimes it would be nice to use a different strategy. But again, on CPython, or in Python in general, we cannot because everything relies on reference counting. So it would be nice to design a C API which allows to be GC friendly so that we can use it if we want. And yeah, why this is a problem? It's what I said before. From the CPython point of view, many things are stuck. It's stuck in the past. We cannot evolve. CPython developers cannot try new things, and this is a problem. The GIL is one of the biggest examples. Removing the GIL without killing reference counting is very hard. People have been trying, and it's always this the problem. And well, it's not the only problem, but it's one problem of the GIL. And as I said, for alternative implementation, it's a mess. And these links, it's a blog post on the PyPy blog, which I wrote a couple of years ago, and explains in very detail why it's hard for PyPy to emulate all these details. So, okay, this was the problem, and now let's talk about the solution, hpy. So, too long didn't read version. Instead of using include Python.h, you use include hpy.h, and you use this new API which tries to solve the problem which I talked about. In particular, it's GC friendly, and it hides implementation details by default, and is designed to be fast on and easy on alternative implementation, because we are developing hpy with three backend in mind: CPython, PyPy, and GraalPython, which is Python and the JVM developed by Oracle. And so by getting an API which works well on three very different implementations, it means that we are making a good job at hiding implementation details. What is the strategy to be successful in hpy? So the idea is that C extension writer needs to rewrite their extension. It's not automated. We cannot automate it. If we could automate it, well, we could just do it inside PyPy in the corner, and we tried and we failed. And but in order to convince people to use it, well, to start with, it should not be slower than the existing solution. Else nobody is going to make NumPy 10% slower just because it would be nice. So if you rewrite NumPy using hpy, the end result should be as fast as now on CPython, at least. And this is, I will explain later how we achieve this. It should be possible to port existing modules incrementally, because, like, again, try to port NumPy as a whole. It's impossible, but the idea is that you can port things one by one module at a time, one type at a time. And again, why should I care about this? Why NumPy developers should do these things? Well, for example, because then it's faster for alternative implementation. This is like the most immediate achievement that you get right now. And eventually, when hpy is it's adopted and is widespread, then yes, we can also start thinking about using it officially in CPython and evolve CPython and try new things. But the most immediate advantage is, well, to be fast on PyPy and GraalPython. The other most immediate advantage is that hpy, because of its design, allows to intercept all the calls and add some debugging information to it. So, how many of you that wrote manually C extension did a mistake with incref or decref? Like, cool, couple of hands. For example, hpy will show you later as a mode in which it automatically catches missing, closing handles, which is the equivalent of missing the graph, and it tells you, okay, you forgot to close this handle at this line of code, and so you have a memory leak, which is very, very useful, and that's another good reason to use hpy right now. Well, right now, we need to be ready, but yes. And finally, another important point is that depending on how you compile your extension, you can get what we call the universal binary, which means a single binary which can be loaded on all Python interpreters. So you don't have to compile it 3 or 4 times. Potentially, it could be even be a single binary for many CPython versions. So, well, much easier to distribute. And as I said, you need to port your code manually if you wrote it by hand. But if you are using Cython, it's getting a backend for hpy. So if you use Cython, you get automatically all the benefits of hpy. And this will be a huge point because a big part of the ecosystem is written with Cython. So automatically many modules will be available on hpy. To get a bit more in details, what is the difference? It's not too much. Like sometimes the C API and the hpy API looks a bit different, but most of the time they look a bit very similar. But the point is that instead of passing objects around and pointers around, we pass handles. And like handles are opaque by default, and it means, for example, that it's like they are similar to file descriptors or Windows capital handle. It's an opaque pointer or something to an object. But the point is that with handles, you need to close them in pair. Like if you have a function call which creates a handle, then you have to close it, and you have to close this handle one time and only one time. With reference counting, for example, this example works. It's fine because I'm at this point in time, the object pointed by both A and B has a reference counting of 2, because here it's 1 when I create, here I do the incref, and then I can decref A twice, and everything works. And this, for example, is what it's incredibly hard to support in PyPy because of the thing that I said earlier. From the hpy point of view, what happens is that this is wrong. You cannot close the same handle twice. We should close A and B separately. And this change alone makes everything simpler for extensions, for, well, implementations. The other thing is that we have this hpy context object, which we pass around everywhere. And it's basically a pointer to the state of the interpreter or something, and it can be used for many things, including, for example, subinterpreters. So now in CPython, if you have to use subinterpreter, it's a problem because you don't have a good way to get the state of the current interpreter, because it assumes that there is a global one. But with the hpy design, every function will get something explicitly that you pass around, so it's correct by design from some point of view. Example of C API. This is a very simple function which takes 2 arguments. They expect it to be integers, and it does the addition and returns the result. And you write it like this. If you raise the hand before, then you know exactly what this code is doing. And the hpy equivalent is not too different. So we have the implementation, and you see that we have the context which we pass. Instead of passing PyObject star, we pass this type, which is hpy, which is the handle. the call to a pyarg parse tuple becomes hpy parse, and you see it's very similar. You have hpy from long instead of pylong from long. You notice that you pass the context around. Instead of py method defs, you have this module defines, but it's pretty similar. The biggest difference is that you have also to add this kind of decorator or something similar to a decorator in C, which is a macro, which does a bit of magic. And because in order to implement hpy on CPython, we need to write what we call a trampoline, so a function which has the this signature, which is what CPython expects, and under the hood calls this implementation. This is done automatically by hpy, but yeah, that's why you have to write this macro. But you see that it's just that it's the same information that you put here, like the name of the exposed Python function, the calling convention, and the docstring, and you just put it here. So just shuffle a bit, add an H somewhere, add the context somewhere, and it works, hopefully. Not quite, but. Okay, this is when you write the code, the API. So the API is what you as a programmer write in your editor. The ABI is what the compiler produces, the binary. And the zero overhead goal that we want is achieved by having multiple targets. When you compile the hpy extension, you can choose which target ABI to target. So if you compile it in CPython ABI mode, all the hpy calls are converted at compile time using macros to CPython call. So in this example, hpy from long becomes statically a pylong from long. And this means that if you go down to its root, so you have your foo.c, and you compile using the CPython ABI, you get something which is indistinguishable, if it's the correct pronunciation, well, something which you cannot distinguish from the original extension that you started from, which means it's fast, and it works only in a specific version of Python, and all the same. But you can also target the universal ABI. It means that we produce something different. In this case, it would be like foo.hpy.so, and this is something which, well, targets the hpy universal ABI, and it's like the universal binary. It means that this binary can be loaded on PyPy, on GraalPython, and on CPython by using this hpy.universal module, which is CPython specific, which is what we develop. And so you get the one binary for all achievement. In the future, nothing stops another Python implementation to add its own header, which is compatible with hpy, which does all the tricks that it wants to make it fast. Like it will be the equivalent of the CPython ABI for the bar Python, which doesn't exist yet. So, like, this is the idea. hpy is the specification for the for the API, but then you can compile it to multiple targets. And to be a bit more concrete, because so far it's like, yes, I'm talking, but it's not easy to understand what's going on. So, depending on which target you choose, you get header file which contains different implementation. So if you target the CPython ABI, hpy from long, it's implemented in this way. This PyPy.h is something which converts a PyObject star into a handle. And so for example, we call pylong from long, so we get a PyObject, and we do Py2h, which is just a C-cast, 0, just to convert the PyObject star into something which has a C type of hpy. And then you see clearly why it is a zero overhead. If you target the universal ABI, what you get is something with an indirection. So we have this context, which is basically a giant virtual vtable of function pointers, and we call this function, this function pointer, which will be provided by the implementation. So PyPy provides its implementation, GraalPython provides its implementation, and that's why it's universal, because of the indirection. That's why we also have a bit of overhead. So if you target the universal ABI on CPython, we measure on some benchmark 5 to 10% of overhead, but it's your choice. Like If you value the fast performance more than everything else, you can distribute your module using the CPython ABI. If you prefer the universal thing because you just have a single binary, you can just distribute the universal. Or you can distribute both and let the user to choose. And let me also show very quickly the debug mode. So imagine to have a situation like this in which I want to increment a number. So this is something that could be, if you remove the h, it's really like a normal CPython extension. So instead of here, I forget to close this object, which I should, this handle, which I should. So it's missing the graph in CPython. It's a memory leak. This is how I compile. So in the setup.py, I basically say that instead of using x modules, I say hpy x modules, and I setup requires hpy.devel. And when I compile, I ask setup tools to target the hpy, the universal ABI, and I get foo.hpy.so. And when I can run it in this way, so using this hpy.debug.leak detector context manager, and when I run it normally, the debug mode is disabled, so everything works. But if I enable it with the environment variable, I get, well, the leak detection for real. So here it says, okay, you forgot to close the handle at that point in time. We are working on the way to get also the stack trace, the 6 stack trace, so that you can clearly see in which part of your code you forgot. I mean, the handle was open here, and you never close it. What is the current status of hpy? We are porting some libraries. So there are ports of UltraJSON, Matplotlib, PSUtils, Kiwi Solver, and the Numpy is in progress. And basically, the idea is that by porting these libraries, we find what are the API that we need to do this work, and we design and implement what we need for this. So it's iterative approach, and eventually we will support all the API, hopefully, but that's how we are doing it. We have the Cython backend, which is in progress, and it will be a huge step forward. We just released 0.0.4. And yeah, as I say, the new API are added on a by need basis. For hpy 0.0.4, it works on CPython and GraalPython, and it's in progress on PyPy. I hope to complete it very soon, basically. Future plans, we want to complete the porting which are in progress and hopefully support more. We want to complete Cython, add the missing APIs, and, well, ask the libraries to merge our work upstream, but like we have talked to them already, like the Numpy developers are very positive about hpy, because they also agree that the current situation with extension is a problem. And also the CPython core developers in general have a positive thinking of it. So we also need to add better tooling to be able to pip install, conda install, everything. But yeah, okay, this is something which happen over the time. And when everything is ready, in some time, we can think about wrecking a PEP and make it like an official API. So I think I'm done in time. Wow, I didn't think that.
You're perfectly in time. Perfect. Thank you, Antonio. We have 3 questions, and we have 5 minutes, so I think we have enough time. So yeah. I'm gonna read it. So, once there will be Cython support, what will the extension written in Cython gain?
They will become automatically fast on PyPy, for example. And well, from the point of view of the extension, that's it for now. Like, because the debug mode is not very useful, because if you trust Cython not to be buggy, well, you don't need the debug mode. But for example, it helps Cython developers to find bugs in their code, for example. And in theory, we also plan to have support for bypassing the argument packing and unpacking, so that, for example, PyPy and Cython itself can call the underlying C function, which is, for example, this, like add the long imp, by passing only directly the C-level values without doing the packing. So even with Cython, it could be faster than CPython, but that's future plan.
Thank you. Second one is very easy, I believe. Why is it called hpy?
H is for handle, because, well, yeah. Originally it was called the Py handle, and then we started to write, and this was Py handle here, Py handle there. It was long, and we, well.
Okay. Abbreviation.
You need to find out the story.
Indeed.
Suggestions are welcome.
How hard is it to try it out? Apart the changes to my extension code, what about the build process?
The build process is easy. It's literally this. What is it? The hard part is to find a slide, but once you find a slide, the build process is that one. You have to modify your code, but you basically the setup requires and hpy x modules instead of x modules, and well, finger crossed, and it works. But we need better documentation. I admit it's not very easy, like in the sense that yeah, you know what to do. We are in the process of writing docs, which will be like a tutorial, like how to port an extension to hpy. The very first step, which is what I'm doing now, including like how to start from a CPython extension to an hpy extension, which delegates everything to the CPython ABI, because as I said, it's incremental. You can mix the two. So, but yeah, we are writing it.
Okay, we have one question on Slido, and then we go the old-fashioned way with Cesare. So, do all Python implementations support context pylon? I mean, there is this the pointer thing, and other interface functions.
Okay, right. Yes. Let me
just
write it.
yeah, because it's more complicated to
pronounce than to read. Like, okay, do all Python implementations support these basically? Where is it? This line. The question is whether all Python implementations support these. Well, it's up to the Python implementation. If they want to support the hpy universal ABI, they must provide a context which contains this function pointer here. And PyPy provides it natively, GraalPython provides it natively. For CPython, we provide an extension module which fills this big context and pass it around.
So you need to modify in some way the original Python implementation, but it's only just CPython.
Yes, yes. I mean, we expect that all the new Python implementations will, write it natively, but for CPython, for now, we provide it as a separate extension module. Eventually, CPython might decide to merge it upstream, but it's a long process.
Okay, my question is about this slide specifically. You talk about zero overhead.
Yes.
But you are relying to the compiler, no?
Yes.
To optimize, because...
Well, static inline functions are macros. We are relying on the compiler to remove this call.
Yes. Wasn't better to just use a macro?
No, because static inline functions are better, and I mean, all the modern compilers...
I know, macros sucks.
Yes.
I don't like them.
I mean, most of this code is automatically generated. We have a specification of the API, and all the trampolines are generated automatically, so it will be very easy to switch to macros if we find it's a problem in performance. But so far, it's not.
Okay, thanks.
Okay, we have 1 minute. Does anyone have further questions?
Sorry, thanks for a great talk. I know it's a long shot. I saw that you kind of have a 2-year-old repository for hpy bindings in Rust. Is that on the radar?
I mean,
not anymore.
At some point we had a sprint somewhere, and someone started it, and yeah, it's not on the priorities.
All right, I think this is it.
Thank you.